Hello and welcome. I see we are just opening up the session here today as we reach the top of the hour. You can see on your screen, you've reached the SCS Executive Education Program Informational Webinar on the upcoming course entitled Deep Learning. In this program, we're going to be able to identify and build the right neural network for solving your biggest challenges today and in the future. So we're going to learn all about this program here from Carnegie Mellon University, School of Computer Science, Executive Education. As we go through this next hour or so together, we're going to be touching on two key areas here today. Firstly, we're going to learn all about the program curriculum. What are you going to be learning? What are those key learning outcomes that you'll be able to take with you at the end of the program? The other area that we're going to be touching on is how is that learning delivered? What is the experience like? What is that day-to-day interaction? So you're going to get insights into both of these areas here on this informational webinar today. We're going to introduce our speakers here in just a moment. From there, we'll talk more about this broader community that you're joining here at Carnegie Mellon School of Computer Science. I'll introduce you in more detail to your co-faculty members who've designed this program, both of them here to tell you all about it today. Then we're going to dive into the overview of the program. What is this program? Who is it designed for? And what can you expect to take away? From there, we're going to talk about the program experience. What is it like to be a participant? We'll talk about next steps. And finally, as promised, we'll get to all of your questions. So with that, I now have the honor and pleasure of introducing our two course faculty members and subject matter experts of today here to tell us all about this program. Firstly, we have with us Rita Singh, who is a professor here at the School of Computer Science, Carnegie Mellon University. Professor Singh, would you like to jump in and say hello to the audience?
Hello, everyone. It's exciting to be here, and it'll be wonderful to interact with you at the end of the session today. I would say that you are in for a very, very, very exciting ride into the world of artificial intelligence. We have lots of state-of-art AI systems to talk about. You will be an expert by the end of this program. And we look forward to being with you throughout your journey into this learning experience.
Thank you so much, Professor Singh, for being here with us. We're so excited that we have a chance to learn more directly from you here today. I know you're joined here by your co-colleague and co-designer of this program, Professor Diksha Raz, who's also a professor of Language Technologies Institute at School of Computer Science, Carnegie Mellon University. Professor Raj, would you like to also jump in and say hello to our audience today?
So, hello, everybody. Good morning, good afternoon, good evening, wherever you are. It's a pleasure to be part of this program, and I'm really looking forward to following you students and interacting with you, making sure all of you get through this successfully. As you'll see in the coming slides, what you're embarking on if you sign up for this course is to learn about what is basically quickly becoming not just a useful tool, but a necessary tool if you want to survive in tomorrow's world of technology. So welcome again, and I'll see a lot more of you in the coming weeks.
Thank you as well, Professor Raj. I'm so excited that we have you both here. Before I hand over that spotlight to our professors, we want to help set the stage for you, give you a little bit of context about this broader community that you're joining here at Carnegie Mellon School of Computer Science. Many of you have some familiarity with the School of Computer Science, but if you don't know, it is recognized globally as a respected international leader and a center for unparalleled research and education in computer science. And what makes the Carnegie Mellon School of Computer Science so special, not only is it home to world-class faculty, as you'll see here today, that offer undergraduate and graduate education and research opportunities that are second to none, along with executive education programs such as this one, but really doing so around what we know works well for learners. So around what we know works well in the neuroscience of adult learning, we're thinking about the ways that we can convey this knowledge across. So the School of Computer Science here is a cross-disciplinary school. It's known for being at the forefront of advanced computer science disciplines, including everything from artificial intelligence, computational biology, human-computer interaction, language technologies, machine learning, robotics, and software research. So you get that cross-disciplinary lens as well. The difference here at the School of Computer Science, we're just so pleased to announce voted number one in artificial intelligence specialty and graduate programs for computer science by U.S. News, World, and Report. So if you're really looking to gain these insights and this knowledge from the number one source, you have arrived at the right place. Carnegie Mellon School of Computer Science is known for its expert instructors, really thinking about thought leadership around practical experience. So how can you bring these concepts to life in the real world in your work? The integration, so there's a suite of interconnected learning modules that really leverage resources from across the School of Computer Science. Engagement is a big part and what you'll be doing throughout your time in this program. Really, the pedagogical approach is structured around what we know works well for adult learners, those small group learning activities that allow you to have direct interaction with instructors and peers, really not only deepening your knowledge, but gaining that broadened landscape of ideas as you see these concepts and themes coming to life for your peers and their industry and their work. So giving you that deep dive into the learning, as well as that expanded scope of understanding. And then, of course, the reputation unparalleled to none as number one worldwide leader in academic research. So certainly at the right place here, studying this important topic here. We have many courses offered at Carnegie Mellon University. This is a sampling of some of those programs: artificial intelligence, machine learning, natural language processing, computer vision, programming with Python, algorithms and data structure, software engineering. Feel free to take a look at our expansive portfolio of courses. If you're a corporate customer, if you'd like to come in with a group, we do offer special group enrollment pricing, tiered discounts, and we will offer your team a dedicated learning facilitator. So later on in this session, we're going to talk more about learning facilitators, what their role is in the program, but this is an additional layer to your teaching team, industry experts who are really at the helm of your day-to-day learning. And if you're a corporate customer, we will have a dedicated learning facilitator for your team, giving you that freedom to really discuss your business opportunities alongside of your learning. So a lot of opportunities here as you think about joining this community at Carnegie Mellon School of Computer Science. So this program in particular, who should attend? This really is the crux of why you're here, to answer this very question: is this program right for me? So we wanted to give you this high-level understanding of who we had in mind when we designed this program, really for those seeking a more sophisticated understanding of neural network architectures and the confidence to deploy their skills to solve real-world artificial intelligence problems. So gaining that deeper understanding, and then also the frameworks for application, really allowing you to bring your conceptual knowledge into a place of real-world practical application. So if you're a software engineer, a data scientist, a technology professional, software developer, an AI or ML professional, this program is going to give you that layer of knowledge that you need in order to deploy these skills and help to solve real-world artificial intelligence problems. Any more questions about program fit? If you'd like to describe a little bit more about your background, we invite you to let us know there in the chat and in the question box, and allow us a chance to respond to you here on today's session. But let us know what's on your mind as you think about program fit, particularly as we start diving into some of the details here in just a moment. So as you think about this program, here's what we're going to be doing. You're going to gain that expert in deep learning and in-demand skill for technical positions in software engineering and data. So there is a slant towards career development. We're thinking about ways in which we can help you to advance your career. And really, for those of you looking to springboard into those career advancement opportunities, this program is really going to allow you to do that, bringing to life your learning in a way that is demonstratable on the job market. So the applications of artificial networks are wide-ranging and include solutions for problems in the language, transportation, imaging, and many more areas across sports and the healthcare industry. So this program begins with a gradual introduction to basic neural network architecture, and then it will advance through more advanced models and more sophisticated concepts that are necessary to solve time-based problems. So with this knowledge, you'll be more prepared to discuss and tackle challenging technical problems that are central to many global industries. So we're thinking of ways of lifting frameworks that are really geographically agnostic, allowing you to take these methodologies into your work, into your geography, and into your industry and role. So those key outcomes of the program, this is what you're going to be able to take away towards the end. This is a 10-week program. We start with what we call week 0. So you'll have an entire week to get to know the learning platform, to ensure that you're ready. You can cover the course policies, get to know your peers and your teaching team, and then we'll launch into those 10 weeks there. You do have access to this program for an entire year. So you'll have week 0 to orient. You'll have an intensive 10 weeks, and we'll describe all what you're going to be doing in that 10 weeks here in just a moment. And then from there, an entire year to continue to touch base into the themes and concepts, into those on-demand videos and those learning topics. But really, those key outcomes here, these 10 weeks are designed to help software engineers, developers, data scientists, AI and machine learning professionals to deepen their technical skills, allowing you to solve more complex challenges and add more value to your organization. So you're going to develop an understanding of deep learning techniques. You're going to understand the structure, the function, and the training of key neural network architectures for building tools and systems. And then you're going to build the confidence to apply deep learning methods to real world problems. Again, really getting you ready for that practical application, giving you that confidence, knowing that you have methodologies that are time tested and available and that will work. Prerequisite knowledge. Many of you might be wondering, what do I need to bring into this program? Do I need some advanced level of technical experience? So first and foremost, you should know the subject matter is rigorous. This is a rigorous program really designed to help you to take this learning into a place of action by the end of 10 weeks. So this is a program that is going to require dedication and commitment. To ensure success, you must have a strong working knowledge of linear algebra, calculus, statistics, probability, and object-oriented programming, including Python. So these are those prerequisite knowledge requirements here. There will be tests in that week 0. So we talk about that orientation week. You'll have self-assessment opportunities. So if you're not quite sure if you have the prerequisite knowledge needed, you'll have an opportunity to test your knowledge and really better understand where you are and if you have the knowledge needed to dive into those 10 weeks. So any more questions about prerequisite experience or knowledge, again, we have our program advisors here with us helping to support today's session. Let us know there in the question box or in the chat, and we'll be sure to help walk you through any of those kind of granular details about your program fit, about your prerequisite knowledge experience, and your readiness for this program. So with that, I now have the great honor and privilege of introducing our 2 keynote speakers here today. Once more, we're going to give you a little bit more detail about your professors and then hand the spotlight over for today's meat and potatoes, the heart and the star of the show, our program overview. So firstly, here we have with us Professor Rita Singh, who you met a moment ago. Her research is in the area of AI-based technologies for advanced human sensing and is currently focused on AI-driven voice forensics, as she's worked in areas of speech and audio processing for more than 2 decades. In 2019, the first edition of her book, Profiling Humans from Their Voice, was published, and it focuses on techniques that apply AI to deduce all sorts of information about a person based on their voice. As she currently teaches 3 graduate level courses at CMU, and she is here designing this program as well, and here to tell you all about it. Joined here by Professor Bhiksha Raj, who works on a variety of areas related to AI as well. His focus is on speech processing and more generally on intelligent systems that can learn to understand and respond to their acoustic environment. He also works on a variety of problems related to the basic theory of applications of neural networks, such as the design of optimal losses, adversarial defenses, and novel problems that may be amenable to a solution that involves neural networks. At CMU, he teaches the primary course, Introduction to Deep Learning, which is taken by several hundred students every year, both within CMU and across the world. He also teaches courses on machine learning for signal processing and quantum computing. Very pleased to have you both here with us today. With that, I invite you all again to put those questions in the Q&A as we make our way through today's program overview. But for now, handing over that spotlight to our professors. Professor Raj, I believe you're going to be taking us away here. Thank you for being with us once again. Over to you for the program overview.
Thank you, Marie. Thank you, everybody, for being here. So I am Professor Bhiksha Raj, a professor here in the School of Computer Science at Carnegie Mellon University. And as Marie mentioned, I teach our primary course on deep learning. So in fact, this course is actually sort of derived from the course that Rita and I teach, which is taken by something between 700 and 800 students every year at CMU. The objective of our course at CMU is to prepare students who come in essentially cold, to be prepared to deal with the industry and with the future rigors of academia, where they may be working on deep neural networks and areas that require deep neural network skills. So, so the course that we will be going over is outlined in 10 modules. Again, as I mentioned, this is a compression of the course that we already teach here at CMU. It's a very successful course. Over the 10 modules, we'll be covering many of the topics that we do in our own course. The course itself is designed not to be just a purely mechanical instruction on how to compose neural networks. Our objective also is to teach you the whys. Why are you doing what you're doing? And where appropriate, some of the historical background as well. So the 10 modules are as follows. We will start off with a module on introducing the concept of deep neural networks and explaining what it can do. We'll teach you next all about the most basic form of neural networks, training multi-layer perceptrons, and the various techniques that you can use in general to train these models. All of these skills that you learn in modules 2 and 3 are going to be applicable throughout all of the remaining modules, and in fact, through the rest of your life if you continue to work on deep neural networks. Then in module 4 and 5, we talk about convolutional neural networks, which are a very important variant of neural networks that are designed for a specific problem of position invariant pattern detection. We'll explain a little more about it when we get to it. 6 and 7 are talking about recurrent neural networks, the kinds of problems which deal with the kinds of problems where the input is some kind of time series data. Again, these are very commonplace all over the world. And when we outline these modules, we'll mention some examples. 8 is about models that can be used for things like machine translation, or maybe transcribing image or captioning images or videos and such like. In fact, the techniques that you will see in module 8 and later in module 10 are what are the basis of many of the latest AI techniques that you're reading about even today. Then in module 9, we will take a look at trying to understand what it is networks learn in the process of learning to perform all of these tasks that we're talking about. And module 10 very briefly goes over all of the latest forms, latest as of the time of this module, of networks and the direction in which the world is progressing. Now, all of the skills that you're going to learn from module 1 through module 10, these are going to be essential and required if you want to be able to work on neural networks. And if our experience with the course at CMU holds here as well, by the time you're done with this course, you should be prepared to take on much bigger challenges than what the course itself throws at you, because you will have all the necessary skills. Now, I'm actually Rita and I will go through the individual modules to tell you what these modules are going to cover. So, Marie, yeah. In the first module, we're going to introduce the problem. Now, deep neural networks began as an attempt to model the process of human cognition. So, believe it or not, models of human cognition go back thousands of years to 400 BC, in fact. The earliest models of cognition was based on what is called associationism. You have almost certainly heard about it because almost everyone has heard about Ivan Pavlov's experiment with his dog. So those were experiments on trying to understand associations and how the brain understands the world around it. Now, the first instance of a computational model of it that we today would recognize as an artificial neural network actually appeared way back in 1873. So at this point, it has been 149 years of artificial neural networks. So you might be surprised to know that, right? So we will actually talk about, it's good to know where we come from. So we'll talk about the original basis of it and the various computational Boolean models that McCullough, Pitts, and later Frank Rosenblatt came up with, because these are the foundations of everything that we do today. So in this process, we will understand the basic unit of a neural network, the perceptron, how it begins as an attempt to model the basic unit of the brain, the neuron. We'll understand its limitations, and then we'll also understand how we can begin connecting these up to perform all kinds of magical things. Now, when we began speaking of AI and neural networks, one of the reasons you're here is that neural networks are everywhere. Although people have been working on neural networks since 1873, they really came into prominence maybe 10 years ago or even less, when suddenly many tasks that were seemingly impossible in the past, like playing really smart games or automatically captioning an image or a video or recognizing speech almost perfectly or translating languages. Although technologies existed for these in the past, they were really very poor. These became mainstream with the advent of neural networks around 2015. And right now, of course, neural networks are taking over everything. There's talk about how these things might even become sentient maybe in coming decades. So this learning about these networks is key. But what is the network? In every single case, the neural network is a very simple function. It takes in some input and produces an output. It might take in speech and produce its transcription. It might take in an image and produce its caption. So at the core, a neural network is a mathematical operation. It's a function. All of these operations that we are speaking of, playing games and etc., they are also performed by functions. And in this module, we'll see how an appropriately constructed neural network can compose pretty much any function, which means an appropriately constructed neural network would be able to perform the functional computations required by all of these magical AI tasks. So in the first module, we see what a neural network is, and we understand that it's what is called a universal approximator. If you construct it properly, it can represent any function. You name the function, you can compose a neural network for it. But that's a possibility. The real question is, how do you actually construct these networks to compute the functions that you're interested in? And in this second module, we'll actually address this problem. We are going to explain how a neural network is essentially a multi-layer perceptron, a layer-wise construction of these basic units called perceptrons, and how the MLP has tunable parameters, and how you can compose a network to compute a specific function by just architecting the appropriate network, having the right number of units connected in the right manner, and setting their parameters in the right way. And so we will be learning about how to do this. Specifically, when we learn these models, we learn these from examples. You will be provided large numbers of examples of the kinds of input-output relations that you want the network to model. The function that the network is computing must capture these input-output relations. And so on these examples that you've observed, any given network is going to compute some output, which may not necessarily be correct. And so the way we tune the parameters of the network is to try to minimize the error between the output of the network and the desired output of the network for each one of these examples. And so we will explain how this whole thing can be set up as a mathematical problem of function minimization, where the function you're minimizing quantifies the error between the actual output of the network and the desired output of the network for all of these training examples, these training instances that you have been provided. We will also understand how this function minimization can be performed using a technique called gradient descent. And gradient descent requires derivatives. Basically, you want to know how modifying any parameter in the network is going to change the overall error that it makes, whether it's going to increase it or decrease it. If it decreases it, you want to make that change on the parameter. If it increases it, you don't. But you need to know this value. Will modifying a parameter, how will modifying a parameter change the error it makes? And this term, this derivative, can be computed using a procedure called backpropagation. And module 2 will also teach you all about how to perform backpropagation through a neural network. So in sum, you will learn that you can compose a neural network to compute any function, but then that the network's parameters must be learned to best compute that function, and that these parameters can be learned to minimize the error that the network makes on examples, and that this minimization can be performed through gradient descent, and that the derivatives required for gradient descent can be learned through backpropagation, and you will learn all about backpropagation.
Hi. So Marie has already introduced me. So in the interest of time, I just want to mention one key aspect of this course or point about this course. It's a complex and I would say slightly difficult to learn subject. However, we have tried to make it very pictorial and visually engaging. So basically what I'm trying to say is that you will be learning mostly through pictures and interacting with pictures. And I think that makes this course very, very special. So anyway, going on to module 3. In module 3, we are going to learn about how to train neural networks efficiently. By training, we mean learning the parameters of the network to compute a desired function. As we just saw, the network itself is learned by providing it a large number of examples and estimating the network parameter values such that the output of the network is correct for these examples. But for this to work, we will need a very large number of examples of training data. The actual estimation tries to minimize the error between the network output and the target output at all of these examples. This runs into many problems. When we have a large number of examples, simply computing the total error or the total loss over all of these examples can be very slow and inefficient. And also the process of trying to minimize this loss can get stuck in local minima, the parameter values that are far from the optimal values that we want, but which locally look like modifying them will only increase the errors. So in this module, we learn about ways to make the learning more efficient. We learn about incremental update methods that update network parameters on individual or small batches of examples, what we call stochastic gradient descent or mini batch descent. We learn about the various stochastic gradient descent. We learn about various constraints on the learning algorithm for this approach to actually give us the correct answers. We also discuss various tricks and heuristics to speed up the training, like momentum. When we train these models, we want them to give the correct answer, and not just on the training examples, but also on the novel data that we give it at test time. So we learn about various methods called regularization, such as batch normalization, dropout, weight regularization, and so on. And these methods improve the generalizability of the networks. So in Module 4, we begin to address a new kind of problem, one where we require what is called shift invariance or position invariance. To understand what is meant by position invariance, consider the problem of trying to detect if a picture has a flower in it. So mathematically, a picture with a flower in the top left corner is very different from a picture with a flower in the bottom right corner. Yet we want the same network to detect both of these pictures as ones having flowers. In fact, we want the network to detect the presence of a flower regardless of where it occurs in this picture. And this is what is called position invariance or shift invariance. We discuss shift invariant neural networks in this module, what are called convolutional neural networks. So we discussed the original biological motivation behind such networks, how they started out as models of mammalian vision. We discussed some of this historical background and how it leads to the architecture known as the convolutional networks. Mammalian vision has two components: a position invariant pattern detector and components that aggregate the outputs of this pattern detector to make it less sensitive to perturbations and noise. We discussed these components and their computational analogs, convolution and pooling. We explained how these work and their mathematical details. We also discussed how to rescale inputs, make them smaller or larger in spatial dimension using convolutions and pooling. These are what are called upsampling and downsampling layers. And finally, we show how to put all of these components together, how these components come together to construct a proper, complete convolutional neural net. We also touch upon two other topics in this module. First, a convolutional network is actually a parameter efficient approach to perform what we call position invariant pattern detection. So we discussed this aspect and the parameter reduction that results from the convolutional approach as well. We also outline how we can train such networks using backpropagation and gradient descent. And so with this, I'll hand over back to Diksha.
So continuing on in module 5, we'll dive into how convolutional neural networks can be trained. So convolutional neural networks, like any other neural network, are trained using gradient descent. We define an error between the actual output of the network and the desired output of the network on our example training instances. And then we compute the derivatives, which tell us how modifying any network parameter changes the error, and adjust the network parameters to reduce this error. So these derivatives are computed using backpropagation. We'll explain how backpropagation can be done in a convolutional neural network, how we can propagate these derivatives back through any final classification layers, how we can backpropagate the derivatives backwards through convolutional layers, and how we can backpropagate them through pooling layers. Again, remember, convolutional layers are the layers that introduce position invariance, and pooling layers are layers that aggregate the outputs of the convolutional layers to introduce robustness to jitter and noise. And then in the process, we will actually show how, when we backpropagate these errors, we have to do two things. We have to backpropagate the errors. The key portion is backpropagating the error through a convolutional layer from the derivatives from the output of the layer to the input of the layer, but also in the process, we need to compute the derivatives for the parameters of the layer. And we will see how both of these themselves end up being convolutions. And so, although the whole process seems very complicated when you first look at it, when you actually look at it from an implementational perspective, these are very simple operations. And all of this is going to be explained pictorially, so it should be very simple. And then in the overall, we'll see how we can use this backpropagation to go through all sorts of layers, including layers that reduce or increase the size of the images or the input. And finally, how all of this can be put together in order to train a convolutional neural network. Another kind of problem, which is very important, is that of dealing with time series data or series data in general. So, for example, if I'm trying to answer a question, when I'm answering a question, I have to read the entire question. It's a sequence of words. So what came in is a sequence of data. Or if I'm making predictions about the stock market, what comes in is the sequence of stock indices over the past several days. So I'm looking at a sequence of inputs to make a prediction. And this kind of problem abounds. Pretty much half of the kinds of problems that you will deal with in the real world have to deal with looking at sequential data inputs and making predictions about them. And so in module 6, we'll begin looking at the kinds of modules that deal with sequence data. We're going to start off by giving you some examples of the kinds of problems that require this kind of model. We will also show explain how models that consider the past in order to make the predictions of the present need something called recurrence, where they have to refer to their own intermediate values from the past, and explain how this recurrence works. Now, in the problem of introducing recurrence into networks, in the process of introducing recurrence into networks, we run into a couple of problems. Anytime you have a self-referential process, it can become unstable. Things can blow up or things can die. The other thing is we are looking at time series data, and the model has recurrence, but the purpose of the recurrence is for the model to remember things. For example, it might be trying to maybe parse a program, and it needs to know that a brace has been opened, and it must hang on to this idea that a brace has been opened until the brace is closed, which could happen at any time. There's no fixed horizon within which this happens. So there's a notion of hanging on to important memory until it's no longer required. And we'll explain how having any kind of naive implementation of recurrence has this issue that things just aren't remembered the way you would expect them to be remembered. Memory becomes a problem. So naive recurrent models have both memory and stability issues. And then we will explain a solution that addresses both of these issues very successfully, the so-called long short-term memory network, which many of you might have heard about. Then when we speak of recurrence, we are always speaking of making a prediction about something based on past values, but that's not the only kind of recurrence. You might also want to look into the future. So for instance, if I'm looking at a string of text and making some prediction about a word in the middle, what part of speech it is, for instance, then it's not merely what came before the word that informs, it's also what followed the word. And so we will also explain in this module how this basic recurrent formalism can be used for making such bidirectional inferences through what are called bidirectional recurrent neural networks. And then finally, we're going to explain how you can train these networks using the standard tools of backpropagation. So I'll hand over here to Rita for the next two modules.
Okay. Okay, so in module 7, one specific kind of time series analysis problem that Viksha was talking about is speech recognition. Here, the input to the network is a regular series of what are called speech spectral or cepstral vectors. And these arrive at the rate of about 100 vectors per second. The output must be a sequence of phonemes or words that can be at any rate. Sometimes we have 20 phonemes in a second. At other times, we speak only 10 or even none at all if a person isn't actually speaking at all. The output has an order relationship with the input. Each word or phoneme corresponds to a section of the speech, but there is no time synchrony. The output has varying rate. In such cases, we need a different kind of recurrent network to analyze the data. And these are what we discuss, or these models are what we discuss in module 7. We explain the problem of time synchrony versus order synchrony and describe how the key to such problems is to know how to align the output to the input. This is key both to train the model and to perform inference with it. We then describe the solution approach, what is known as the connectionist temporal classification or CTC framework. It is important to point out here that CTC was a landmark innovation. It is important. It is important in many ways. It was landmark for speech recognition, and almost all modern speech recognition systems today use it in one way or the other. It is also used in handwriting recognition systems. You will learn all about that. The module goes into details not only on the architecture of the CTC model, but also how to train it and how to perform inference with it. The CTC model is actually a probabilistic model. It attempts to find the most likely word or phoneme sequence for example, for an input speech recording. Finding the most likely output is actually a search problem. And you'll learn all about the various strategies that we use in search problems, such as greedy search and beam search, etc. So in Module 8, there is another very important kind of sequence analysis problem that we address. One where the input sequence doesn't necessarily have any monotonic relation with the output. For example, consider machine translation. If you're translating from English to, say, German, the input to the model is a sequence of English words, and the output must be a sequence of German words. The word order in the two is not going to be the same. Or consider a dialogue system. The input is the user statement, and the output is the system response. There may not be any word level correspondence between the two. And in these cases, we need a new kind of model called an encoder-decoder model. This module, Module 8, discusses such models. We discuss many important concepts in the process. We discuss how to use language prediction to derive numerical representations of words, what are called embeddings. We discuss how to use these for language modeling. You may have heard of models like GPT-3, which can generate entire stories. You'll learn a bit about how that works. We discuss the lack of synchrony I mentioned, how this can be handled by separating the input and output processing with the encoder-decoder model. The encoder processes the input and the decoder processes the output. We discuss the very important issue of attention as well, how the decoder learns to pay attention to the most appropriate regions of the input at any given time. Attention is a very important concept that drives most of the recent models. So we discuss this in detail in Module 8. And finally, like in the CTC model, the model tries to find the most likely output for any input. This is a probabilistic inference process. We'll see strategies, including greedy and beam search strategies for it. Encoder-decoder models with attention apply everywhere, including tasks like image captioning, video captioning, image generation, etc. So this module, Module 8, is a key module. And with this, I'll hand over to Bhiksha again.
So in all of this, by this time, you would have learned, by the time you get to Module 9, you'd have learned about various kinds of neural network models. And if you follow up with the quizzes and the homeworks, also how to implement them and how to make them work, we would have learned all about the hows. We would have learned a lot about the whats, but not exactly what goes on inside these networks. How exactly does a network perform the task that it does? What does it learn in the process internally? So as we know, a neural network is this network of perceptrons, all kinds of components. Those components must be learning something, and can we actually put those to some other use? This Module 9 is going to address this issue. We're going to see how, when you train a neural network to perform some kind of a classification task, what you're actually doing is training a statistical model that performs maximum likelihood estimation. These may look like complicated, fancy words, but surprisingly enough, by the time you get to Module 9, you will know all about how to do it, even if you haven't encountered the terms earlier. We'll also see how this very complicated and yet simple model, the neural network, does something magical. It's a feature extractor that can take all kinds of very complicated data and somehow convert them such that the classes can be separated by hyperplanes. We'll also look at what it is the individual neurons in the network might be learning, and we'll explain how these individual inputs that the individual neurons are learning can in fact be used to reconstruct the input. And so these networks, in which a network, the neurons derive some information from the input, and then where this input is used right back to reconstruct the input. These are called autoencoders. We learn about autoencoders. And in an autoencoder, there are two modules. The first one is where the input is analyzed and the neurons capture some information about the input. And then there's a second component, which is the decoder, which uses this input, this information to reconstruct the input. And we will see how the decoder and an autoencoder is something very surprising. It ends up being a generative dictionary for the class of data that the network was learned on. So for example, if you learn this network on music from a guitar, the decoder simply ends up being an artificial guitar of sorts. It only produces guitar sounds. So we will see examples of this kind and how and the implications of these interpretations. So Marie, can you go to the next? Yeah, thank you. So based on these, we finally get to module 10, where we begin looking at more advanced problems. First, we go back to the attention and encoder-decoder architectures that we learned about in module 8 and adapt those to the recent, latest, greatest architectures that everybody is using for pretty much anything these days, which is the transformer architecture. We will look at transformer architectures and the components of it. By this time, we will be running out of time, so we will be seeing a lot of advanced architectures in this module. We won't get into too much detail, but you should still be in a position to understand enough to be able to maybe read papers or systems and implement them yourself. So we will understand transformers, how they work, and how they can be put to use for various tasks. Now, one very special class of data are graphs. In most of and nearly all of the things you would have seen so far in the course, you would have been working on things like text, on speech, on images, which are all nice sequential or well-patterned arrangements of data. Graphs don't have that kind of structure. And so we will look at graph neural networks, which can actually deal with data that are graphs. Then we will look at statistical models, the variational autoencoder, which is an extension of the autoencoder we saw in module 9, which can be used to characterize probability distributions. This is probably one of the more important uses of neural networks that you may not have heard of because it lies behind the scenes in many, many problems. And then something that you almost certainly have heard of, you must have seen all kinds of news about deep fakes, about people automatically generating pictures and images and even videos and whatnot. All of these are done using what are called generative adversarial networks. These are, in fact, just an almost intuitive extension of the variational autoencoder framework that you'd have just seen previously. And so we will learn about generative adversarial networks and contrast their properties with variational autoencoders and see what these things are capable of and how one might go around trying to implement them. So that is the totality of the 10 modules. And hopefully by the time you get to this point, you will be, if you've gone through all the work, you will be sufficiently conversant with the topic that you should be prepared to go off and deal with much more complex problems than you will during this course because you have all the tools and the skills.
Thank you so much to both of our professors for being here and taking us through this content with such detail and really invigorating information here. Really exciting to see what you've put together and very honored to be here learning all about it. So thank you both. Our professors are going to be staying here with us until the end of our time together to help answer questions. So if you do have any questions, please place them there in that Q&A. We're going to be getting to those here in just a moment. But let's step into the program experience, give you a little bit more detail into that day-to-day experience and what it's like learning here in this program. So there's a few key components we want to call your attention to, but just to set the stage here, we follow a pedagogical approach that we call bite-sized learning. And this is a chance for you to learn in an immersive environment at your own pace around a schedule that works for you and in real time. And so what this looks like is at the beginning of each week, a set of content is released for you and your peers, and you have an entire week, a 7-day period to make your way through that content. That content contains a lot of what you see here on the screen. There are on-demand videos, knowledge checks, assignments, simulation, role play exercises, discussion boards, all of that contained within that content aimed at helping you to really take your learning into a place of action. So throughout that week, you're going to start by watching on-demand videos from your professors that really describe these concepts in detail. From there, you'll step away from those videos and you'll immerse yourself in a variety of these activities to really roll up your sleeves and tinker with these ideas and bring your learning to life. You'll be doing that shoulder to shoulder with a cohort of peers. So as you deepen your knowledge and you understand the program, you're also going to be learning as you see how these same themes and concepts come to life for your peers. So this program is highly interactive. We depend on one another. It's a reciprocal learning environment. You can bring your questions, you can bring your curiosities and get those addressed in real time throughout the week. This is not what we call a massive open online course, which is a course where you can go and learn some tools and frameworks and apply them. This is a highly specialized program that's really based around relationships. It's really based around allowing you to have a place that extends beyond the scope of what's possible in a traditional classroom environment. So in a traditional classroom, you're bound by space and time, right? You have a certain number of seats in the room, a certain number of minutes, and a certain set of curriculum to get through. Here in the online world, we're able to break down those barriers in space and in time, allowing you an immersive learning environment where you can learn brief on-demand segments, apply that knowledge, and have that sort of interactive and engaging experience throughout the entire time. So it's a really exciting program, and it's delivered in a very high quality setting that helps you to engage with your full teaching team, including your faculty who you met today, as well as learning facilitators. We mentioned learning facilitators a little bit earlier on in the session, but these are industry experts that come into the program and guide your day-to-day experience, sort of like a teaching fellow, if you will. They give you individualized feedback on your assignments. They host weekly office hours, a chance for you to get your questions answered, turn on your video and your audio and engage in real-time discussion. And they're really there with you every step of the way, a place for you to go to really deepen your learning and get your questions answered. So all of this here for you. You have access to the program, as mentioned before, for an entire year. And if you were to take away 2 keywords here as you think about, what is the program experience? It's highly interactive and it's highly convenient. Those are our 2 words that really describe it here. You're able to access all of this content from a mobile device. So you can learn on the go from your smartphone or your tablet. And there's a lot of bonus content on advanced topics. So if you discover a niche area of interest you want to explore further, you'll have those additional resources right here in the program. So in addition to gaining all of that knowledge, in addition to gaining those relationships and broadening out your professional network, you also have an opportunity here to earn a credential from Carnegie Mellon University School of Computer Science. This is a sample of that digital certificate of completion that you have an opportunity to earn here in this program, really helping to formalize your training and showcase your learning and your knowledge in this area of deep learning. So, again, just to iterate, for those of you looking to springboard into career advancement opportunities, this program is really designed to help you do that, to bring your learning into a place of action, have some tangible takeaways that you can show in the job market, and really aim to help you to bring this learning into your career and into your profession. What's next? How do we get started? This is our last slide here today, and this is where I have the chance to introduce you a little bit further to our program advisors who are here with us on the call, helping to support your questions and your chat. Our program advisors are the course experts when it comes to all of the logistics for this program, the dates, the time. If you'd like to get those live webinars on your calendar in advance, you can ask our program advisors. They can help produce those calendar holds and get you all set up to go for the program. They're experts in the course policy. So you might be wondering, how are the assignments graded, or how do I earn that certificate of completion? What's the evaluative criteria for the program? These are the types of questions your advisors are best situated to help with. They can also help with all of those registration and enrollment questions. And we want to make sure you have everything that you need in order to begin this program. So if you're interested in flexible and transparent payment options, special group enrollment pricing, some of the corporate courses, or the corporate discounts, or the additional courses that we talked about before, get in touch with our advisors. They're going to be able to help walk you through those details as well. So how do you get connected with a program advisor? If you haven't done so already, they're there in the chat for you. But if you go over to the course website, you'll see the link there at the bottom of your screen. And also in the chat box, if you open the chat, you'll see a link right there that you can click on. It'll take you right over to the course website. On the course website, you'll be able to get connected directly with a program advisor using an app we call Calendly. You may have heard of it. And it allows you to select a time that works for you in your time zone to make that connection as simple and easy as possible. So go right on over to that course website, select a time to meet with a program advisor. The website also allows you to download the full course brochure. That's everything we talked about here today and more. It's a comprehensive end-to-end scope that tells you everything you need to know about this program. And then finally, you can begin the application process right there from the website as well. We've also provided an email address for you there in the chat. That's cmuscs@emeritus.org. If you'd like to get connected by email, certainly send us a note there. I'd like to invite both of our speakers back in here for any final words of wisdom. We sort of reached the top of the hour. We've closed out our questions here today, but we'd love to hear any final words of advice for students who are interested in joining this program. Maybe we'll start with you, Professor Raj. You're on my right here, so we'll start with you.
Okay.
And then
So,
Singh.
thank you. It's again, I'm kind of excited to see how this course goes. What I can assure you, the students, is that if you stay with it and you complete all the assignments that we have given you, we expect that you will be well situated to actually deal with at least the beginning of a career in deep neural networks and AI going forward. So we will always be available for you. If you have any questions, any general advice, not just on the course, on the specifics of the course, but on the broader area of deep learning and related topics, we're always going to be here to answer your questions or advise you.
Thank you, Professor Raj. Over to you, Professor Singh. Any final words of wisdom to leave us with here today?
Well, I'm very excited to see how this course pans out as well, and I echo Bhiksha's thoughts. I am confident that if you work hard and if you go through all the assignments, and you at the end of the course, you will feel competent enough to be able to understand the newer AI technologies that are coming out. You might even be able to create your own new kinds of systems, and you I think will understand the excitement and the growth that is happening in the AI field. So that has been our goal in designing this course, and I hope we achieve it at the end of the day.
Thank you so much to both of our professors for being here. Again, such an honor to hear from you both about this program. Thank you for designing it and putting it together and making it available globally to all of you here with us. Thank you as well for joining here today. We hope to see you back in the program. We'll be signing off with a heartfelt good morning, good afternoon, good evening, and good day to all of you from around the globe. Thanks again for joining, and we hope to see you soon in the program. Bye-bye.